In this video, we're going to discuss pointers, which are one of the most important things in C++. So what is a pointer? A pointer contains the memory address of a variable. A variable directly references a value, such as count here. A pointer indirectly references a value. Referencing a value through a pointer is called indirection. It's kind of like, think of a box and think of the contents of the box. Well, the pointer points to the box and then there's the contents. The count directly references a variable that contains 7. Count pointer points to the variable space that contains 7. So in the following declarations, int star, which is the terminology used to declare a pointer, count pointer, and int count, the variable count pointer is of type pointer to int. That's what this out is read, pointer to int, and is read count pointer is a pointer to int. Variable count is declared to be an integer, not a pointer to an integer. The star in the declaration only applies to the count pointer. Each pointer variable name must be preceded by a asterisk. Consider the asterisk associated with the type rather than the variable. Int star space p as opposed to int space star p, which is how they did it in Old World C, but it's not a great idea. Star in a declaration isn't an operator. It means the variable is a pointer. They can be declared to point to objects of any type. You can have string pointers, char pointers, etc. So, initializing pointers. Pointers should be initialized to no pointer, which is new in C++ 11, or to a memory location either when they're declared or in an assignment. A pointer with the value no pointer points to nothing and ignores a no pointer. However, a pointer that is unassigned could point to literally anywhere. So pointing it to no pointer is a good idea. From this point forward, when we refer to a no pointer, we mean a pointer with the value no pointer. Prior to C++ 11, you could use 0 or no. You can still do it, but it's probably not the best idea. 0 was used by convention. No is what was usually assigned to. The value 0 is the only value that can be assigned directly to a pointer variable without casting the integer to a pointer type. So, use no pointer. The unity operators ampersand and star are used to create pointer values and dereference pointers respectively. So, the @ operation. This is kind of the inverse of the star. The @ is a unity operation that obtains the memory address of its operator. So, assume the following declaration. We have y set to 5 and a pointer to y, which is currently set to null. This statement assigns the value of y to pointer y pointer. Y pointer equals ampersand y. Y pointer equals the address of y. And here, now we've created a pointer to y. It uses indirection to access the location in y pointer and retrieve its contents by saying star y pointer, putting it in front, will indirect it. So let's look at this again. The address operator is a unity operator that obtains the memory address of its operator. So, int y is 5 and y pointer is null. This statement assigns the address of y to a pointer, and so we get this situation, and then star y pointer will give us access to this. The figure below shows another pointer representation in memory with the integer variable y stored at memory location 600,000 and a pointer variable y pointer stored at 500,000. So this is making a point. Y pointer points to y, but the location of y pointer is at 5,000. So you could have a pointer to a pointer. The operand of the address operator must be an L value. It can't be applied to constants because it doesn't really make sense, especially since memory is often indirectly associated. The unity operator, referred to as the indirection or dereferencing, more often dereferencing, returns an L value representing the object its pointer operand points to. This is called dereferencing a pointer. A dereference pointer may be also used as an L value on the left side of an assignment. So here we have our first pointer sample. Let's take a look. Sample 1. All right, we did something very basic here. Here, in our first line of code, we create a variable I and set it to 7. We create a pointer to an integer and set it to null. And then we create another pointer, which we're going to call bad idea pointer. So let's output our stuff. I equals endl. I pointer equals, it would be null pointer, which in this case interacts to 0. Bad pointer idea equals some memory address we don't even know what it's pointing to. Let's get the address of I, which is ampersand I. Okay. So now let's assign the address of I to a pointer. I pointer equals ampersand I. And now we can get the contents. First, let's print out I, and then it's the address. Now let's look at I and the pointer, which is its value. So now let's modify the value using an I pointer. If we say I pointer equals I pointer times 2 and then print it, we get I now equaling 214. And the address is unchanged as well. So basically we've modified the memory location. We've dereferenced the value at I pointer, which points to I, changed the value. Now I pointer is still pointing at the same variable, but it has a different value. We could also print out I right here, and we'd still get 7. So when it comes to precedence and associativity of ampersand and of dereference and address of, the address and dereferencing operator are unary operators, and they're just below parentheses, brackets, and scoping operators in terms of precedence. So, pass by reference with pointers. There are 3 ways in C++ to pass arguments to a function: pass by value, pass by reference with reference arguments, and pass by reference with pointer arguments. Pointers are used to modify one or more variables in the caller, or to pass pointers to large data objects to avoid the overhead of copying the objects. Because pass by value copies the object. If we got a really big object, we don't want to pass it by value. Use pointers and the indirection operator to accomplish pass by reference. When you wish to modify an argument when calling a function, pass the address of the argument. The function signature must be expecting a pointer. So here's another example. Let's go to our example for pass by reference. And here in this example, we've got a cube method passed by value, which was a copy, and a cube method passed by reference, which takes a pointer. So we'll look at both here. So, get a number by 5, we pass it by value, and get a new result, and there we go. In the pass by reference model, we get a number, we pass by reference, this time sending in the address of number, and not using a return value because we're going to modify it, and then we print it out. So here's our pass by value function, which is just like you'd expect. It multiplies it 3 times. And here's our cube pass by reference, which takes the contents and multiplies it by 3. Now, one thing you could do, if you wanted to make this a little cleaner, would be to have this guy, cube reference, pass by reference, call cube pass by value, and then assign its value to here. Just a little optimization. So, in the pass by reference, the calling function can examine the value function calls results before modifying any variable values, including its own. Next example passes the variable to cube by reference, and with a pointer argument, the address of the number is passed to the function. So here's an insight to think about. Technically, all arguments are passed by value. Passing a variable by reference with a pointer doesn't actually pass anything by reference. A pointer to that variable is passed by value and is copied into the function's corresponding value. So the pointer is copied. So if you wanted to actually modify the pointer, you'd have to send in a pointer to a pointer. The caller function can then access that variable in the caller simply by dereferencing the pointer, thus accomplishing pass by reference. So here's some examples. Before main calls cube by value, it's got a number, we pass it by reference, and afterwards we've got number receives the call, and it goes through and it computes it, and then it will come through and return the value, and it will store it again, and boom, there you go. Number has now been updated. In the pass by reference case, we send in the number, send in the address of the number. So inside the function, we have to dereference the pointer, right? And then multiply it 3 times. Okay. But we're actually modifying the actual variable. We're going to set number equal to 3 times the number, or the number times itself 3 times. And then we're going to exit the function, but number is now actually changed as opposed to sending back a return value. So, many possibilities exist for using or not using const with function parameters. We want to look at the principle of least privilege. Always give a function enough access to data in its parameters to do what it needs, but no more. So, there are 4 ways to pass a pointer to a function. We can have a non-constant pointer to non-constant data, non-constant pointer to constant data, constant pointer to non-constant data, and constant pointer to constant data. Each combination provides a different level of access privileges. Highest access is granted by a non-constant pointer to a non-constant data. The data can be modified through the dereference pointer. The pointer can be modified to point to other data. Such a pointer declaration, like this, int star count pointer, does not include the word const. So now if we have a non-constant pointer to constant data, a pointer that can be modified to point to any item of the appropriate type, the data to which it points cannot be modified through that pointer. So here we say const int star count pointer, and we read this as count pointer is a pointer to an integer constant. Or more precisely, count pointer is a non-constant pointer to an instant constant. So constant pointer to non-constant data always points to the same location, but the data can change through the pointer or through the variable. Pointers that are declared const must be initialized when they're declared. If the pointer is a function parameter, it's initialized with a pointer that's passed to the function. The minimum access privilege is granted by a constant pointer to constant data. Such a pointer always points to the same memory location. Data at that memory location cannot be modified via the pointer. This is how a built-in, i.e. C++ basic array, should be passed to a function that only reads from the built-in array using array subscripts and doesn't modify the built-in array. And the way to declare it would be const int const read from left as a pointer is a constant pointer to an integer constant. So we have another important variable here is the sizeof operator. The unary sizeof operator determines the size of bytes of any data type during the program compilation. When applied to a pointer, sizeof returns the size of the pointer in bytes, not the built-in array size. Operator sizeof can be applied to any expression or type name. When sizeof is applied to a variable name, which is not a built-in array's name or other expression, the number of bytes used to store the specific type is returned. The parentheses used with the size of operation are required only if a type name is supplied as an operator. So, pointer assignment. A pointer can be assigned to another pointer if both pointers are the same type. Otherwise, a cast operator, normally a reinterpret cast, must be used to convert the value of the pointer on the right of the assignment to the pointer on the left. The exception to the rule is the pointer to void. Any pointer to a fundamental type of class can be assigned to a pointer of type void without casting, void star without casting. However, you cannot dereference a void pointer. The compiler knows that an integer pointer is 4 bytes, and it points to 4 bytes. Similarly with other types. A void pointer simply contains a memory address and no idea what's at it. You can't dereference it because the compiler doesn't know the data type stored at that pointer. You have to cast it to another type. So, comparing pointers. Pointers can be compared using equality and relational operators. Comparison using relational operators are meaningless unless the pointers point to elements in the same built-in array, because they'd be next to each other. Pointer comparisons compare addresses stored in the pointers. Common use of pointer comparison is determining whether a pointer has the value null pointer, 0 or no. Another pointer example I want to walk through. Yes, it's using the size of operator. So, for example, here we've got a double, a pointer to a double, a string, and a pointer to a string. So, and we've created a simple structure, and with 2 fields, which we've defined up here, and a pointer to that structure. So, if we run it, we'll see the size of the double is 8. The size of a double pointer is also 8, because on most modern machines, the size of the pointer is 8. The size of the contents is at pointer is also 8. Similarly with a string, the empty string has a size of 1 because you allocate a byte. The size of a string pointer is 8, and in the case of this string, test string with 19, the contents of a string pointer is 40. The reason it's so big is because it's ringing as double byte characters. So pretty much double the size plus the size of the terminating value that's hidden. So that's basically how the size of operation works. And that will get us set for pointers.